Now, what influences delta in order to differentiate whether the complex is going to be in the low or the high spin state? So one thing that does is the nature of the ligands on the metal. Okay, and so we have what are termed strong field or weak field ligands. So this is called the spectrochemical series. And the spectrochemical series is actually more extensive, but for the purposes of this video, I have truncated it a bit. Now, on this end, we have what are referred to as weak field ligands. Okay. So these will promote a high spin state versus those that are on the opposite end, or have a stronger field, are referred to as strong field ligands. And these will promote formation of the low spin state. Okay? And these, one of the general properties that we see for weak field ligands is that they tend to be pi donors. And weak field ligands, importantly, are going to result in a small delta O, okay? Versus over here, these tend to be pi acceptors, and they will yield large delta O. Okay, as an example, we can take the case of hexachloro iron 2, FeCl6, 4 minus. Right? Chlorine is a weaker field ligand. And so when we look at our electron configuration for what is an iron 2 complex, right? So in other words, this is going to be D6. What we expect is that delta is going to be small, so we expect, in other words, delta O is going to be less than the pairing energy. And so what will happen is that we go 1, 2, 3. The fourth electron will go in the EG state, in the EG set of orbitals. 5, and then on the sixth electron, right, it has to be paired with another electron either way, so it's going to fill the lower energy orbital. And so what we end up with is an overall spin 2 system, and LFSE of 1, 2, 3, 4 times -2/5 plus 2 times 3/5. Okay, that's going to be -8/5 plus 6/5 equals a -2/5 delta O ligand field stabilization energy. Okay, now let's compare that to another D6 complex where we just change the ligands to, for instance, cyanide. So we're going to look at ferricyanide. Right. In this case, right, being stronger field ligands, this is going to have a larger crystal field splitting energy. And so in this case, right, delta naught, got get this out of the way. I got 2/5 delta O. Right. In this case, delta O is to be greater than the pairing energy. And so we go 1, 2, 3. The fourth electron, right? Since the pairing energy is lower in energy than the difference in energy between the T2G and the EG, it's going to be more energetically favored for it to pair. And so we have 6 electrons in the T2G orbital, in the T2G orbitals, which means we have an LFSE of 6 times -2/5 delta O equals -12/5 delta O. Okay? And so what we see is that from the ligand field splitting energies, this has a greater ligand field splitting energy, but right, we're going to have different spin states between these two. Oh, and I forgot the spin states. The spin state of this is also going to be 0. Okay. And this has consequences for the stability of the, this has consequences for not just the spin state, but also potentially the reactivity of the complexes.